Guys, thanks for sticking with us. I hope you guys are having fun. I'm going to continue this track with Mark McClain. He's going to be talking about IPv6 in OpenStack. So with that, Mark.
Oh, yes, thank you. Welcome. So, all right, so a little bit about me. My name is Mark. I am the CTO at Aconda Inc. We are a spin-out out of DreamHost, which is based here in LA. Our offices now are up in San Francisco. I'm a member of the OpenStack Technical Committee. I also was been a core reviewer in Neutron since the Folsom release, as well as I was the technical lead for Neutron during Havana and ISAL cycles. So, IPv6. What we're going to do is take this kind of in two parts, and we'll start with the IPv6 part. Adoption is increasing. If you take a look at this graph, this is the V6 traffic that Google is seeing over time. If you notice, just look at the increase between 2014, and even more recently. Or if we compare that to take a look at IPv6 traffic, say in the US from Akamai, if you look at around 10% of their traffic 6 months ago, now it's trending up to almost 13%. For those who, like, hey, this IPv6 thing, am I using it? If you're doing it right, you may not have noticed, but you're actually getting IPv6 service if your laptop is configured to use it here. So that if you access any IPv6 ready sites, depending on how you configure it, it might be the preference. Now, one of the things is that, when you think about IPv6, the standard was first proposed, and they started working on it in 1993. They first proposed one of the first drafts in 1995. So, this standard's 20 years old, and we're just now getting around to it. A couple of the differences which have made some challenges is it's a huge address space. Good thing is it's 128-bit. With v4, we're running out 32-bit. Basically, the registries are nearly out of addresses. If you look at that, that's a lot of addresses. Basically, if you were to take something the size that was like an inch square and said that's the v4 address range, if you wanted to then say what the size of the v6 address range is, that's essentially the solar system. In terms of size comparison and space, I think everybody on planet Earth could get something like 10 to the 28 number of addresses personally. So if you want to start putting IP on grains of rice, it's doable. You get end-to-end connectivity. No more NAT, no more proxies, no more address translation. It's direct end-to-end. Configuration's a little bit different. We'll dive into that in a second and why that matters, especially when you start talking about OpenStack in the cloud. Routing is a little bit different as well because the way it's configured, the way it's set up is tweaked a bit, as well as what the routers will do for you. As well as you'll see an increase in usage of ICMP and multicast as well. Those traditionally were not used in v4 networking, but for v6 they're critical components, especially at the link level. So when we talk about configuration, especially auto configuration, one of the things you'll notice with v6 is you get a link local addressing. If you were to do an ifconfig or an IP addr show, you're going to see an FE80 address, and that's the auto-configured link local. The nice thing is that when you're on the network with v6, you don't have to have a pre-configured address to start talking to other hosts on the network. Generally, that address is generated via Slack, which is based on the EUI64 address or your MAC address. It's a well-known algorithm. You take the 48-bit MAC address, convert it into 64 bits, and then attach and then prepend FE80. Now, if you have a publicly routable address, how that's given to your station, if you're doing Slack-based, is via a router advertisement, and the prefix is announced. That prefix, we'll talk about, it has to be a certain size, but that way, so when you when you plug your laptop into the network here, you're not getting a DHCP lease as much as your computer's being told, hey, this is the IPv6 prefix available. With Slack, it's got to be at least the 64, and then go configure yourself. And given that range, what will happen is you take the MAC address, you generate it, and then you detect to see if there's a duplicate on the network. And that's generally how the auto configuration works. That's how your addresses are generated. If you're very privacy-minded, you may notice something that your Slack address is based upon your MAC address, which means you are trackable across networks because that last 48 bits is routinely predictable. In theory, most MACs are, mostly unique, but then again, you can spoof MAC addresses too. It's very easy to pop open your laptop and have your Wi-Fi card advertise, well, anything. So When we talk about auto configuration in v6, there's, one of the things is router advertisements give you the ability to say what the prefix is, to say where the default router is. And that router, when in routing, is a link local. It's not, you're not advertising the, basically the router advertisement tells all the stations, it's like, hey, I am the router for this network, send me your packets. If you want to use DHCP v6, they added that as option as well, and so there's two modes for that. One is stateless, so what you get is you get the router advertisement with the auto-configured address, but what they realized is that with router advertisements, you could not pass extra options to certain clients. So maybe you wanted to pass options for TFTP, like where to boot from, if you wanted to download an image, if you want to do any, and so what you could do is you could do RA and then configure a DHCP server that basically in the RA bits you say, here's your address, but oh, by the way, make a DHCP request as well to get additional information. And that way you get the auto configuration side as well as you get the ability to pass extra options. In terms of stateful, that's basically traditionally what you would find with traditional DHCP now. With v4, it's an assigned address, comes out of a pool, it's picked. Whatever algorithm the DHCP server wants to use for it, it's really up, and it works with the same similar exchange. Now, routing for v6 is a little bit different. One of the things is that the actual headers and the packets are a fixed size. It makes processing a lot easier. You don't have, they've also cleaned up some of the fields. There's no checksum in an IPv6 packet. Mainly reason being is to guarantee the lower level at the link layer is going to have checksumming as well as TCP, obviously, and UDP, and v6 are required to do the checksumming. So that they decided it was redundant. The nice thing is when you don't have a checksum in your IP packet, you can decrement TTLs, you can rewrite the packet and keep moving it without having to recompute a checksum. You only have to change the header bits. Another one of the things you'll find is that no more fragmentation. So in a v4 network, if you have a difference in the path sizes and MTU on each side of the router would be responsible for fragmenting unless you set the do not fragment bit. In v6, there is no do not fragment bit. The packet, if you send a packet that's too big, you get a control message back that says your packet's too big, send some, and then you're supposed to send something smaller. But now the routers don't have to fragment packets. You don't have to worry about packet assembly, reassembly. What happens if you get fragments? No longer have to worry about that. Talked a little bit earlier about router interval sent out onto the link local address to say, hey, I'm here, I'm a router, here's the prefix, and send those out at a regular routine basis so that when clients come on board. Router advertisements can also be solicited as well. Typically what you'll find is you can, when you have a new station comes up that does a neighbor advertisement and basically is doing a duplicate address detection and via Slack, and it'll say, hey, this is my address, the router will recognize you have somebody trying to detect for a duplicate and typically will preemptively send a router announcement. Another one that changes is you'll see ICMP v6. It's a little bit different. It's also more integrated in terms of what you would find with v4. You have several critical things which occur on it. One of them is neighbor discovery. Before in v4, that would be it's actually part of the protocol versus ARP before was running at this quasi 2.5 layer, where it was, part Ethernet, part IP. Router advertisements, I talked about those. And some of the messages require multicast, and so multicast, there's a set of reserved groups. So like, for instance, if you wanted to, ping all the hosts on a particular segment, if you were to ping 6 FF02, : 1, it will basically, it's the equivalent of doing a broadcast ping. Another one of the advantages, another one of the things is I talked about, which was path MTU discovery. So again, both endpoints are aware of what the actual maximum path size is, and then that way the packet size from the sender is appropriately set for that one that can reach the receiver. Before v4, you can actually be sending too large of packets, and somewhere in between that's getting fixed for you, and you may not know that you're sending traffic suboptimally. So, there have been a couple challenges. I mean, this standard's been around for 20 years. It takes a while to get there, and one of those is, got to deploy new hardware, also develop new hardware. For a while, for some of the routers, you were getting v4 processing was done at hardware, and the v6 was actually being done in software, and so you get a dramatic speed difference, as well as, updating software applications to take advantage of it, application updates. and that's where it gets hard, as well as, just in general, some of the addresses aren't necessarily as human-friendly as they could be. So how do we represent these, going through that? Fortunately, when you have DNS, you have discovery services, you can somewhat get to the point when you're doing auto-configuration where these addresses aren't important. That said, given the growth of IPv6, given the fact that traffic's increasing, and when you take a look at Akamai and Google, which are very large providers, it's time, and if you're not doing IPv6, it is a must, and if you're not designing new deployments with it, you really need to go back and start again and design it, because, traffic is being generated. Residential ISPs are installing v6, and activating, my grandma's house has v6. She doesn't know she's got it, but she's got it. So, it's here. It's no longer, this thing forward in the future. It's actually here. So, having introduced and talked about IPv6 and some of the differences a little bit, let's talk and kind of switch gears to the other half of the equation when we're combining IPv6 and talk about OpenStack and Neutron. So for OpenStack, if Monty touched on this a little bit earlier this morning, but it's a large ecosystem of projects. You have some common projects which you see across all the clouds in terms of compute, identity, networking, and storage. It's released every 6 months, like clockwork, mainly, as Monty said, because we release on a timeline, not on feature sets. And again, just like Monty, there's varying, if you talk about OpenStack, you have to show this logo, so here's how all the components fit. I also like to look at OpenStack a little bit differently, which is you have an end user who's using a compute API, a networking API, and a storage API. These APIs are agnostic to the actual technologies that are behind them. So really, compute API could be backed by KVM, could be backed by ML2 plugin, or say storage with Ceph. But from the end user, they don't know what they're doing. They don't know what's going on behind the scenes. They're just getting cloud services that they're accessing either via the OpenStack dashboard or CLI or the APIs. So when we talk in terms of what specifically is Neutron, it's a unified API for networking. It has a very small core. Reason we did that is we wanted to ensure that it was available everywhere, regardless of which extensions were available, because it supports a pluggable architecture that also allows deployers to choose extensions appropriate for their deployment. You will find Neutron in both public and private clouds. Kind of the canonical diagram of what Neutron looks like is you have a server, a REST service, which is backed by a relational database, talks via messaging queue to various agents. The L2 agents run on each of the hypervisors and are responsible for managing the layer 2 wiring on each of the hypervisors for the guests. The layer 3 agents are responsible for managing and routing layer 3 DHCP agent, and in advanced services such as load balancing or VPN as a service. So when we take a look at what specifically IPv6 support in Neutron, one of the things we've had for a while is we've had IPv6 IPAM. This was supported almost since Folsom. Wasn't very elegant, because basically what we did is we said you provided a /64, we would just assign addresses sequentially and keep it. We didn't use Slack. You had to have basically special images to understand how to use it. Auto configuration wasn't supported. RA wasn't configured. We did support security groups. Also, and more recently, L2 pre-population, so that way if you're running overlays, you can intelligently pass traffic through the tunnels. Like I said, support started Folsom Grizzly timeline with very early support. More recently in Juno, we've added some advanced enhanced support. From the tenant perspective, because when we start talking about clouds, it's like, I'm a deployer. Why do I want to enable IPv6? And for many people, it really comes down to two things. First one is no more NAT. You get in-host connectivity. You don't have to deal with NAT. You also don't have to deal with floating IP. So if you work in an environment with a very constrained IP space where you don't have a whole lot of public IPs, what you end up doing is creating, a jump host which has your public IP and then a constellation of hosts behind it, which you can't really ever talk to directly. With v6, you can now set that up real easy. So tenants like it because they can instantly type SSH v6 address and get instant connectivity without taking extra hoops.
So you can start remembering these.
So you can start, yeah. Or you can cheat and use Nova, and Nova SSH, if set up right, will appropriately look up the name and do the mapping for you. Yeah. That is the one downside is, yeah. Or a big, massive alias file. So, yep. So if we were to take a look at that, yep, there you go. Your nice, very human consumable, direct SSH. So.
Can you add some Neutron itself, some kind of DNS server for that?
So there is a companion project in the OpenStack ecosystem called Designate, which is working to provide DNS services in OpenStack. It's a companion project and it's in pairs with Neutron, but is not part of the Neutron project. I believe it does. So when we talk about Juno, because like I said, we made lots of enhancements. It was released last October. One of the bigger changes we made is in terms of configuration. We wanted to support the three options that you would find in a real-world deployment. So this, even though this is the cloud, your tenants are setting up logical networks, logical deployments. We wanted to make sure we match those. So the main difference, if you're familiar with OpenStack, is we introduced a couple new attributes, which I had kind of in that dump on the side, which is IPv6 address mode, IPv6 RA mode. One influences how the IPAM and Neutron selects addresses. The other one influences whether or not we actually turn on RA for you. So if you're running Slack, we run RA. We basically spin up RA DVD inside of the network namespace in your router, and it does the announcements, and magic happens. If you can go with DHCP-v6, we support both stateless and stateful, but we're using DNS mask to support those. So typically what you'll find, so if you were to take a look at how those would run, say, in a real deployment. So when you have routing, you have a network node, and this is the reference implementation. I mean, Neutron has something like 28 different plugins available in different combinations, going up to 32 publicly available by the end of Kilo. So if we take a look at the reference implementation, you have hypervisors. Somewhere you have a network node that sits in between, which then talks into the core of your data center. Typically, the network nodes are bare metal host, basically running a Neutron L3 agent that creates lots of Linux network namespaces to do routing. The reason we use network namespaces is Neutron supports overlapping IPs, and namespace is the only way to get independent IP stacks per tenant. So the L3 agent provides support, and typically if you're having RA, the RA instance is going to run inside a namespace within a network node. One of the challenges with that is that you have a static external network gateway. So this is kind of one of the limitations of Juno, which is I've gone in as a deployer, I've configured the IPv6 address space for a particular tenant, but what I also have to do is I then have to go tell my routing infrastructure that this tenant's external address, I have to go configure the routing upstream. That's one of the shortcomings in Juno, which is we don't automatically set that up. We're not using any kind of dynamic routing or any kind of even coordination with external routers to share that information. Yep.
So Neutron supports overlapping IP. So if it is IPv6, the client outside will see the same IPv6.
So if you're doing overlapping IPs, that's where you can't, if you're going to do overlapping, and what some folks have done is they only allow overlapping IPs in the ULA range, which in IPv6 land is the equivalent of RFC 1918 space. So you can go through and select private client, and they only allow overlapping IPs there and won't route those externally. Downside is you don't get end-to-end connectivity. The reason they're doing that, or even if you allow overlapping IP ranges for v6 for tenants even in publicly routables, they're maybe setting up a CI pipeline or a lab pipeline, and so they deliberately have not set the upstream routing the same, or they've manually configured routers to adjust for the fact that there's addresses. That's one of the unclean parts in terms of, that's why routing is not dynamic right now.
Is there an option to turn off the overlapping?
There is a flag that you can turn off overlapping IPs, and some for IPv6 have stressed that that's what we should just do in general. But one of the problems, again, if you're doing any kind of, say, CI pipeline where you need to build up an entire logical deployment and with specific IP addresses, you should take a look at your application and architect differently, but that's a different story. Some people want to replicate production, which is fine. So you have that, and then also, you have other alternatives manually. You can configure 6-to-6 NAT, where you're actually doing prefix NAT and just having the router replace wholesale prefixes. Generally, though, there's other ways to get around that, especially if you have applications who need routing like that. One of the other, and the provider network is also another support we put in. So one of the largest, I think, IPv6 deployments for OpenStack is Comcast is doing some work with it. They use more of a flat, so they have a provider router upstream, which is announcing RAs, and so what we did is provided a hook to make that happen, and especially for those running flat networking. A couple of security considerations for IPv6, because a lot of people kind of get a little scared because you do have end-to-end connectivity. A lot of times for many, many years we've been using NAT as a security blanket, but it's a very horrible security blanket even for v4. Don't think it actually keeps you safe. It's kind of like putting a deadbolt on a screen door, you know? So don't, you know, you got to have a real security policy. Think about this. And your security considerations for v4 and v6 are the same. Make sure that you have sane firewall rules, that you are using the security groups provided in Neutron to provide, you know, to allow access to your instance as you want. You also, additionally, can run IP tables or any kind of firewalling inside of the guest as well. Or if you have an edge firewall set up, you can filter there. So there's lots of opportunities to ensure a good policy.
And as you mentioned, there's IPv6 addresses are statically assigned, right? So it would be easier to...
So the v6, yeah, you can assign them because you can allocate a port in advance, and so you know specifically exactly, you know which port and you know what IP that's going to set up to be. If you're, say, running a load balancer, you can create VIPs, and so you have those available. Another one, the security considerations, and these really go together, which is DHCP spoofing and RA spoofing. DHCP spoofing is no different than what we do in v4 land. You know, spin up a rogue DHCP server and start handing out addresses, and you know, make yourself the forwarding device and start inspecting everybody's traffic as it passes through. Same with RA. RA is actually even easier. You just start announcing yourself as a router and a prefix, and you can start sucking traffic. So, real question is, do we care in the cloud? Maybe. You know, it depends, and we'll take a look a little bit about that, because in certain cases, if you're in a private, isolated tenant segment, that's something you have to balance, because there's also performance characteristics. So, when we talk about the management layer of Neutron, this is all the control plane, this is all the back-end systems. In terms of API readiness, you know, we can stick a check mark on the API layer. The HTTP interface for Neutron can be run over v6. It works fine. HTTP, HTTPS works over v6. The database layer, obviously, if your database has most of the Python backends work with v6. Client libraries are v6 ready from, you know, the Neutron client is available. RabbitMQ, which is pretty much the de facto messaging bus for OpenStack, works with v6. And overlay tunnels, we kind of have a check mark. This is kind of an incomplete one because we have to take a look at, it really kind of depends. So when we talk about setting up tunnels in Linux and we're using the 3.9 kernel, we're using IP root 2 utilities, it's going to work. You can have a v6 tunnel endpoint, you can set up your VTAP, and it's going to be fine. Traffic will pass, traffic will flow, it will behave normally. So if you're using the ML2 with Linux Bridge, you're fine. If you're using ML2 with, say, OVS, it doesn't work. So for the most part, if you're running the trusty LTS, that comes with Open vSwitch 202, which does not allow you to set a remote IP that's not v4. The fun part is the command will silently pass and succeed in the command line until you go digging in the logs and it tells you that that's not a valid IP address. 202, yeah, I haven't, they made some tweaks in 2.3 and 2.3.1. I just haven't set one up in the lab to really play with it. So I'm not sure, and looking at changelog, I don't think they've hit that yet, but. So, yeah, so typically you're going to find 2.0.2 in Trusty. 2.3, if you're running Ubuntu, is only in the Vivid release. So it's super bleeding edge. So, but for the most part, if you're running LTS, you're probably not going to have v4 support yet. So Kilo, you know, it's coming out in April. So we're doing some work with it currently. We're supporting, one of the changes we're making is supporting both v4 and v6 options. Sometimes you want to, depending on how the DHCP request is passed, you actually want to return different sets of options, even if it's essentially the same host, or maybe you want to pass different options to the entirety of the subnet, depending on how the request comes in. So we wanted to set that up. Another one of the changes we're making is to allow multiple prefixes for subnets. So with RAs, what you can actually do is you can actually announce multiple different prefixes, and all the hosts will get addresses and configure themselves for each prefix they receive. So it's a very easy way to renumber a subnet. You just start announcing a second prefix, have all the hosts wait till they get the RA announcement. They'll update their addresses, and depending on how your applications are set up, if they're set to receive it, unless they're bound to a particular IP, you'll have the ability to renumber a subnet. Another one of the changes is to support external prefix delegation. Basically what this means is, I touched about it a little bit earlier, is right now when you do a when you have a router namespace in the L3 agent, you have to provide the public network that it's going to be, or the external network it's connected to. And what we do is currently we're assigning an actual public IPv6 address to it. But the thing is really you don't need that. You can actually use link local, and as long as you make link local the next hop from that namespace, traffic will appropriately flow as long as the next hop understands how to return. So basically what that's setting up is the ability to do, you know, a link local default external gateway. So one of the fun things, and just a little bit of one of my favorite little oddities at Linux at sometimes. So if you turn on, you know, accept RA because you want to have link local forwarding and you want to get that message, and then you turn on, you know, hey, let's start forwarding IPv6 traffic, what actually happens when you have this configuration is the router will not accept RAs anymore, because you've turned on forwarding, so it assumes it's a bad idea to accept RAs, which is good, which is why we have the, you know, 0's off, 1's on, and 2 is like really on. So it is in the document. I don't think documentation says really on, but it's like, you know what you're doing. But that's one of my favorites. It's like, no, I'm really telling you to turn this thing on. So we have some challenges still. You know, Kilo's getting us there. We're not all the way there. And some of these challenges are kind of external to us that we have to kind of figure out. One of them is the metadata service. You know, typically if you're using a Cloud Init based image, it's going to go look for its default, you know, it's going to go use IPv4 and use the EC2 kind of well-known address of 169.254.169.254 to request, you know, say, any user keys it needs to preload, any kind of metadata services at boot. In the case where you're running v6 only and not a dual stack network, config drive is your friend. Basically, if you're not familiar with what config drive is available from OpenStack operations standpoint, config drive is basically a read-only block device that maps out all this data for the guest. The other nice thing is that there's no real failure of waiting for the network to come up or any kind of wiring. The guest can immediately configure itself because it's reading from a block drive. Generally, also, folks like config drive because it's very secure, because you're essentially reading a read-only block device and not having to send random web requests out that can be easily caught and spoofed. Privacy extension. So I talked a little earlier when I said that, you know, your Slack address is identifiable if you're using the MAC address to generate it. So what happens, and what happens in a lot of IPv6 stacks, is you can generate and use a temporary address for a limited configured amount of time. If you were to go look on your laptop now and you say, you know, what is my IPv6 address, it's probably going to come up with the private temporary address versus your well-known preferred address. This makes it harder for people to track you across and say, like, you know, I was in this coffee shop yesterday, I'm going to be in this coffee shop tomorrow, because they have a reasonable idea. Where it gets tricky in the cloud is when we have spoofing prevention turned on, a lot of what it does is it says, hey, for this port, only this IP address and MAC combination is allowed to be used. The problem is that the address being generated is being generated randomly by the client, and so we either have two choices. We have to write code which snoops out the RA, which snoops out the duplicate address detection and realizes, hey, this client's now talking, we need to go update the spoofing rules, or we either have to ask that clients turn off, you know, privacy. the privacy extensions, which you can go in the kernel config and turn it off. The question really becomes is, do servers really need privacy? Depends on what you're doing with your server. You know, if you're deploying something with a well-known address and everything's inbound, probably not so much. If you're doing other fun things, you know, legal things, you might want some privacy. So from cloud operations standpoint, you kind of have to balance that. And so this is where we kind of get into this question of like, do we care about whether spoofing's turned on or not? Maybe if it's a private network segment, I don't really care. If a tenant wants to, you know, have their instance talk whatever address, as long as it's within their prefix range, I don't care. So a lot of times what you'll see in clouds is they'll turn it off. They'll turn off spoofing prevention on private networks. And some of the more paranoid admins and DevOps people will go back and turn this back on, but the faults you'll find. If it's a shared network, you probably do care very much because typically a shared network is going to be multi-tenant or at least multi-project even in an enterprise. And obviously if you're on a publicly connected network, a lot of times you want to lock down who's doing what. Like I said, you can snoop for the advertisements and update your records accordingly. Also, this gives you an idea of, you know, for logging purposes, which tenant owned which IP. One of the challenges with routing is prefix delegation. There's a little bit of work to use the prefix delegation extension. So this is kind of like how your home router gets its v6 address. It contacts the cable company, phone company, and says, delegate me a block. /64 is given to you, and upstream it's all set up to route and make sure that your next hop understands how to forward traffic back to you. For Neutron's purposes, if you can't randomly have your router image do this and not have it recognized by Neutron, because there's lots of bits within Neutron that need to set up. If you're turning on snooping, it needs to know which addresses, which prefixes are assigned. So one of the challenges is like, how do we do prefix delegation? We kind of started tackling it a little bit or talking about it in Kilo, but then realized that just within a 6-month period is so short because effectively it's 3.5 months of development time. Is that, you know, how we do IPM and prefix delegation, because as a deployer, maybe I've got a /40 that I want to carve up and I want to allow tenants. How do I give them a /64? The last thing I want to do is have random people and say, okay, here you go, here's a /40. You go pick something in that range and you manually enter it. It's just asking for, you know, pain. So we talk about, you know, prefix delegation, how we wrap that up, how we can support that, how we do static routing is one of the problems as well. You have to have a well-known address right now in order for it to work, or you have to manually have configured the upstream router to know the link local address that forwards traffic back to. Some of the other initiatives are to start supporting dynamic routing within Neutron, at least for the router, and either speak OSPF or BGP internally. Both work. I've done both. I would, you know, they're well tested. They're well known how they work, and well integrated with, you know, routers and switches. So when you start taking a look at all these challenges, you realize that it's, you know, there's not a solution upstream Neutron project today, mainly because community is hard. It takes time. It takes time to come to consensus. But we're all running real public clouds, and we need to, real enterprise clouds, and we need to get these things running. So just a little bit, I touched briefly. I want to just touch a couple slides on Aconda, which is an open source project that is Apache 2 licensed. It provides dynamic routing via service VM. So if you want to do prefix delegation with IPv6, you can do that today. You can layer this on. It's a drop-in replacement for Neutron Layer 3 and DHCP and metadata. It's in production now. It was created by the folks at DreamHost. Now, like me and some other folks who were there, we've spun out and are running the Aconda project. It is an open source project. It's available, so it gives you the ability to get more IPv6 support now while the community figures out, you know, how do we support these things. The nice thing is, since it's a drop-in replacement for now, you're not really committing yourself to pain of having to convert or merge code down the road. But it handles all these things pretty seamlessly and pretty easily. We have a GitHub project for it. So kind of architecturally, if you take a look, this is that same diagram I showed you earlier. In terms of Aconda, what it's essentially doing is running one service which manages the service VMs which provide DHCP, RA, metadata services, as well as routing. So. Yeah, so basically what you do with Neutron now is you go in and you change your L3 routing plugin to be a Conda, and you make one small change to Nova that puts a small wrapper in Nova, so Nova's aware that it's managing network service VMs. And then that's essentially...
You can use the Conda even if you're only using IPv4?
Yes, you can use it. It routes, it handles v4 as well. So like the Dream Compute Cloud is full v4, v6 dual stack. I think it's the only public cloud doing that currently, fully. Yeah, so it's been informing our direction. It's also been a great test bed. I mean, we started the project 2 years ago and have been, worked on it internally. And, from our standpoint, we decided that we didn't want to keep it all to ourselves. We wanted to share it with other folks because it is actually useful as more folks are deploying v6 now. So that's why we started. Yep. So, and with that, I guess I talked super fast today. Any questions? Yeah. You have to make config drive on the images. You have to, Cloud.net, you have to configure it for the specific address that you want. But what we found is that sometimes people will, in clouds where they bring their own image, they may be using a previous existing baked image that doesn't understand config drive. Yeah, so some really don't config drive because it's a bunch of operating systems, like running one button and finding where it is. Yeah, I mean, it's older images. Most newer images with Cloud.net know how to do it. But it does support it. It was just one of those things where people asked and we're like, sure. I mean, the pain of doing metadata services is actually of proxying v4 isn't that high.
Is DreamWorks located in LA?
DreamHost, yeah, they're based in LA.
Are you guys doing the same stuff that MetaCloud is doing?
No, we're doing a little bit. So MetaCloud is based on OpenStack, but they're doing slightly different. Yep, but they're still OpenStack based. Yes. So if you want to, as long as it's on the same network, so if you're using the same prefixes, you can just attach them to the network, and then you can go through and you can request and say, for fixed IPs, you just request the IPs that you want, and then Neutron will assign and reserve them for you. The other alternative is you can reserve one. If somebody's running port security, go through and just set a CIDR range that says, here, this port can talk, whatever the range you want it to speak, and then you don't have to reserve every little IP. It is kind of nice, though, from the IPM perspective, if you're using the sequential allocator to make sure those are removed from the pool, or you can actually shorten down the allocation pool. Okay.
Where do I find the documentation to start this from?
The documentation, docs.openstack.org. Yep, and they've revamped all of it, but it's docs.openstack.org. And I'll make that. They're going to publish the slides as part of the conference. I'll also push these up to SlideShare and attach that as part of the notes. I forgot to put that in there.
Conda's pretty well documented.
Conda does have internal documentation also, as well as you ping me offline. I'm happy to talk everything about it. Yep.
So you work at DreamHost?
I worked at DreamHost for a while. I worked at Yahoo, and then actually came back to work at Conda when they spun the company out.
But then Conda spun out from DreamHost.
From DreamHost, yes.
Like the Inktank stuff.
Exactly like Inktank stuff. Yep.
Cool stuff gets special attention.
Yep.
So, but can you talk about, because I've seen Carl Perry's presentations on the DreamHost, what is that, Dream Compute platform, where he's detailed out this OpenStack implementation for, multi-tenant web hosting. I wasn't clear, what is the status of that product? Is it like full GA release or internal?
So Dream Compute is available, and you can go sign up for it today and create an account. Straight away. Yep.
And that's internally, it's all v6. Right?
So internally, the components, some components are fully v6 on the management plane. Some are dual stacked still, mainly for some historical reasons. But as far as from the tenant perspective, it's fully dual stacked. You can do both v4 and v6. So I mean, it's from a development standpoint, even after after I left DreamHost and was still doing OpenStack work, I would still use the cloud because the v6 addresses everywhere were so much nicer than having to deal with floating IPs on other clouds. So, yep. Alrighty, thank you very much.